All right. So far we have mostly been dealing with a nice and pure functional world where everything is immutable and it's nice and dandy. And we write pure functions that we can test and we can trust, and they are stable. Now we're gonna look at the evil dark side of mutable state. I'm kind of saying this tongue in cheek because we definitely need some mutable state when we are doing real world programming. So this is I'm not quite serious, but a little bit serious. In fact, this is a point where we actually have an unwritten rule in the group that if you want to use mutable state in your application, you have to come and ask for permission. And then we can look at it together and see, do we actually need it? We dislike mutable state a lot. But sometimes we need it. And there might be many valid reasons for it. And sometimes it might not be a fully valid reason, but it's just the best way to do things. Like doing something else might just cause you to do a lot of extra work for really no good purpose. But one needs to be very careful with it and consider it carefully before introducing mutable state. Remember that when we talk about parallelization, not having any mutable state means that we can easily parallelize our code and get a guarantee that we will get the same result back as in the non-parallelized version. If we, on the other hand, we have mutable state lurking around somewhere, there are no guarantees. It's almost a guarantee that it will not give you the right answer back. So dealing with parallelization and mutable state is tricky, really tricky, and one needs to do that with a great deal of care. Anyway, enough propaganda, and let's see how do we do this. Well, it's very easy. If you need to have mutable state in your program for whatever reason. Maybe it's to talk with the outside world, and you need to talk to C# in some way, and it's dealing with mutables, or if it's for some optimization purpose, or if it's for convenience. This is how you do it. Let mutable x equals 0. So we just give the mutable keyword in front of after the let and say this is mutable. Right? So we need to do it explicitly. And now x can be updated in the code by saying x 1, x 42, and so on. So we use this backward arrow. Now we could actually look at this function here, and well, it's defined like this, right? So what's the type of this thing? Well, it's something which takes an a, generic a, which is this value, and it returns unit. It doesn't return anything. So what should it return? And this is really when you read code, and this is important, whenever you read code where you have a function taking some argument and returning unit, and that argument might be unit, so you can have functions from unit to unit. Every single time where you have something returning unit, you have something which is doing I/O. Otherwise, or nothing. If you have a pure function which returns unit, then it's not doing anything useful. It's just a constant. So most likely when you encounter a function returning unit, that function has been doing some kind of I/O. It might have been mutating a global variable, it might have been reading from disk and updated some mutable structure somewhere, but it has been certainly been doing I/O. On the other hand, if it returns a value, that is no guarantee that the function didn't do I/O. So, and that's a little bit of a concern, that you can actually write code in F# which will do both I/O and return a value. It's not advisable. In Haskell you can't, so that's one of the really beautiful features of Haskell, is that in Haskell you cannot perform I/O. You can't mutate variables, you can't call databases, you can't communicate over the network, you can't read files, any of that stuff, except by doing so explicitly, by return, and then you have a function which not returning unit, it returns I/O of some type. But that's Haskell. In F#, we're a little bit lax on this, which is, from a practical point of view, if you just adhere to the same rules of not doing I/O and in where you shouldn't, then it works out nicely. And in the few cases where you actually need to, it's convenient. In Haskell, it's highly inconvenient. You have to go through lengths to do a little bit of cheating, and you spend an inordinate amount of time quickly on things that should be super easy. So there are trade-offs. Right, so that was mutables. That's really all there is to it. We have an alternative to a mutable, which is a reference cell. We can say let y equals ref42. So by using this ref function here on 42, it will return something which is called a reference cell. And now y can be updated with this guy. Say y, well, y is 1 now, right? I'll get to it. You'll see why this is a really useful property. And then I can say, well, okay, fine. If I want to use this value which is inside of this, say print I can say bang y. So this is the accessor thing by using this bang. So colon equals to update and bang to access. In this case, we only need special syntax to write it, but we can just read it like any normal value. Reference cells need this special accessor thing to pull stuff out. Now, what is this thing? Well, it turns out that a reference cell is really quite simple. It's defined like this: type ref of some type t equals let's see, mutable v of type t, and that's it. So it's a record type containing this one element. Oh, sorry, I should have something like, this v here, right? Right? So it contains this value of type t, which is mutable. And what this ref does is that it will just create one of these record types. And what this guy here does is it's a function which will open up this thing and mutate the value inside it and close it up. And this function here will pull out v and take the value from it. And you can implement those yourselves. It's a very simple exercise. So what's the point with these? Well, why would you need this thing? Well, the nice thing is that the reference cell is an actual value. So suppose I say let a equals 5. Oh, sorry. Let a equals ref 5. And I say let b equals a. and then I say B equals 10. Now both A and B have been changed. Because they are referring to the same thing. So this is the usefulness of reference cell. If I, on the other hand, if I would do a let mutable x equals 5, and then I say let mutable y equals x, and then say y 10. I have only changed y and x is still having the original value. So that's the use case of reference cells, which allows you to create a mutable thing and pass it around and globally update it. So, while we're on this topic, this is a little bit of a side track, but it might be good to know when dealing with the outside world, particularly with interfacing to other languages, is that we have a way of passing things by reference explicitly in F# using a keyword called Biref. And it has also some inref and outref. So Biref is a bidirectional keyword, meaning that whatever you get, you can do whatever you want. With inref means that you could read only, and outref means that it's write only. So if you would ever have that need, I've used it on a few occasions in a couple of years, and so it's like rare. This is already in the uncanny valley side of things, depending of course what kind of work you do. But I just want to show it. So I can do a function like let f, and then I can say x. Let's see, I get this right. Yeah, so say biref or inref, outref, whatever you want. Biref type of, say, string equals. So this is a function f. It takes an argument x. I say that I will get this x by reference, and then now I can say x get it updated to foo. So if you need to pass a mutable as a mutable to some function, this is the way you do it. And you want to have a function that mutates it for you instead of doing it where you are and using a pure function, and then so there's usually, like if you're in a pure F# world, you might probably end up in a situation where you want to do this, where you have a mutable and you want to send that mutable down somewhere, get it changed, and get it back. To me, it sounds like a bad idea, but there might be some good reasons for it. Most typically, if you are dealing with the C# code, you might want to do this. Because if you have a mutable and send it into a function, the function will see it as immutable, so you can't change it. And you can't say mutable x. So this is the way to say that you'll be able to mutate this thing. And the way you can use this is we can say, well, okay, let mutable s equals hello. And then I can say f, and then I use ampersand s to say send in the address of s to be mutated. Right. So I wonder if we should just cut this here and then no. The next is so short that it's no point really in splitting this up into. Right. When dealing with I/O, and that's also mutable variables, references, and so on, the things can go wrong in ways that we cannot control. and then we need to deal with exceptions. And F# has exceptions too, and they're sort of pretty straightforward. There's not very much to say about them, but typically when we're dealing with pure code in F#, whenever we have a situation where things can go really wrong, we use the option type or the success type if we need to pass back an error message. But a lot of the C# code that we're gonna, or general .NET code that we're gonna end up using, using third-party libraries and so on, they throw exceptions around like toxic candy. So we need to be able to deal with that. So the way this works is that if we have we want to read a file. There's no way we can know whether that file exists when we run the program. Like when inside the program, we have no idea. So we're gonna try to read a file, and if it doesn't exist, like we can check that it exists. But while we checked it, and we actually want to read it and open it, it might have disappeared. So we can't really be very. It's not safe. Like network connections might fail in the middle of a 1 GB transfer, it's just gone. And what we will get back then is an exception saying now something went terribly wrong. So wherever we are doing I/O, we should probably wrap that inside a try block. So we do try, and then we have an indentation to make it a block, and then we can do whatever code we want inside the exception block. I recommend. It's very easy to say, oh, okay, so I just put a try at the top and then, but actually usually you have a lot of definitions and stuff that can't accept, and then you have this little piece where you're doing the actual thing. So keep that in mind. Put your let bindings up here to make all definitions, and then you do the stuff that you want to do that can accept, and you try it, and if it goes wrong, you catch it with the keyword with. And with will receive an exception E, and we can do some things with it. E will contain the message, it will contain some text string, it will contain the stack trace, it will contain all kinds of things. This is actually a pattern matching, so we can have multiple with cases here. Or we can say with E, file not found exception, and IO exception, and and all of these get their own, just like a normal match block. We can just do pattern matching on this E and see what kind of exception it was to deal with various cases if we need to. Or if we don't care, we just do an underscore and we'll be done with it. So that's it. And there's also a alternative to with that you can do, which is called try finally. And the finally will get executed always. If you get an exception, it will execute. If you don't, it will execute. So this E that we get, this exception, or EXN, it's often called in code. So we have with EXN. This here inherits from it's an object in the .NET world, and it inherits from system exception, right? And you can make a class when we get to the object-oriented bits. I'll show you how to make a class, and you can inherit from system exception, and you can create your own exceptions if you want to. I have never done it, and I don't think I will ever do, but never say never. And then you can you can have control over your exception. Now, what do you do when you finally get an exception? Well, if it's an error that you need to deal with, you can do a retry, or you can do whatever you need to do. If you don't know what to do with it, you can raise an exception by saying raise and then you can just send it back to the next layer, X, and just let somebody else deal with it if you don't know what to do with it. And if nobody deals with it, well, your program will crash. Or if you want to create a another kind of exception, there's a nice function called fail with. Fail with. It takes a string, which is your error message. Fail with error. You can of course put whatever you want inside of this. I'm using the wrong color again. So this one is a useful thing, because this will raise an exception, and this function has a particular type signature. It takes a generic, sorry, not a, sorry. It takes a string and produces a generic a. And this is cool. So this is actually a thing with a generic return type, which means that you can take this function and put it in anywhere in your code. Whatever you need. Which means that when you are doing prototyping of things and sketching up things, you can say, well, okay, let my func, and you don't, and it takes x and y, and you know that it's going to have 2 arguments and it's going to do stuff, but I don't want to implement this quite yet. Now you can just say fail with oops, and now you can actually compile the code, but if you ever try to use this thing, it will throw an exception at you. There's a similar one to this one, which is called invalid arg. Which does pretty much the same thing. So that's in case you get invalid values inside your, and you check and you can send them invalid arg. So this is useful in more than just raising exceptions in when things actually go wrong. This is a really nice way of just putting a sort of a little placeholder which will compile but never run. I use it all the time. I think that's a really good thing. And that's pretty much all there is to exceptions. And when we have dealt with object-oriented programming, then you know how to create your own. That's it.